So just picking back up from where we left off, again, this is, as we've seen many times before, for a variable force, the work done can be just so a force varying with distance. So let's say we have F as a function of s, that is to say the force changes with the distance we're at. Before we were thinking of just a constant force, right? So we've got this thing, we're applying a constant force s to it always as we move this distance s. But what if actually the force changes over that distance? Well, then all we do is we find the area under a force distance graph. So instead of just multiplying f by s, we find the area under a force distance graph. Remember how that is exactly what we're doing, just for a constant force. Really what we're doing is finding the area under a straight line graph of f versus s, force versus distance. And all we can do is that when that force is changing, we just find this area here. And that's the work done. By which I mean, if we move to a distance s here, here, then all of this area, this is the work done. And we can see that if we've got a straight line, so we've got a constant force, F is just constant, then obviously the area again is just, the work done is Fs, just as before. But if we've got a changing force, and the area is under this purple line here, then it's this area, and we actually do something called integration to get that area, but you don't need to worry about that now. But you could potentially just read off what that area is by, maybe it's a triangle or something, or it's a parallelogram. You could work out what that area is. And that would be the work done, or the change in energy of the object, of the object or the surroundings, etc. Maybe you've done work against friction. Maybe you've given done work against gravity. All of those things require work to overcome. Maybe you've given it kinetic energy. And that's what your work done, the change in energy, because as we said before, energy before must be the energy after. So the change in energy is the work done. That's really important. We're going to see that now by looking at kinetic energy. So we've already encountered this, and it's just the energy an object possesses due to its motion. And we saw the formula was given by Ke, or Ek, depending on which one you like, is a half mv squared. But why is this? I kind of just plucked that out of nowhere, right? I told you that's what it was, but we didn't say why that was. And we can actually see why that's what it is by thinking about work done. And it's actually a really nice little proof, so I'll do that for you now. So there's a clever way to do it. And the first thing you need to do is to realize that every object of the same mass, traveling at the same speed, has the same kinetic energy, regardless of how it got to that speed.
Hey guys! To continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.